Welcome back, and this is the second in the series of videos going through the chemistry packs. So you're going to need your electron structure notes and a pen and a calculator. So this electron structure pack carries on from the atomic structure work you've done in the previous topic, but we're looking in more detail at how the electrons are arranged. This is very important in chemistry because it's actually the number of electrons and how they are arranged which determines the chemical properties of the elements. So it's those electrons which hold the key for chemistry. If you want to study the protons, then that's more of a physics topic. We kind of consider the nucleus as a ball of positive charge, and we leave it at that. But we need to go into quite a lot of detail about the electrons, how they are arranged in their shells and orbitals. Now, from GCSE, you'll be familiar with a dot-cross diagram. If you're not familiar with dot-cross diagrams or you've forgotten them from GCSE, please pause the video at this point and go back and find a GCSE textbook or a YouTube video looking at dot-cross diagrams because it's really important that you understand those. So if you're staying with us, then I'm assuming that you are quite happy with dot-cross diagrams. And we're going to do two dot-cross diagrams. I'm going to do one for sodium and one for chlorine. So sodium is a metal. It's on the far left-hand side of your periodic table. Remember the big number at the top, that is your relative atomic mass number. The number I'm interested in this case is this number at the bottom. This is the atomic number. And because we're dealing with atoms, it means that the number of protons is the same as the number of electrons. So this also tells me the number of electrons I've got to put in my shells. Chlorine is over the other side, and chlorine has an atomic number of 17. And because again we're dealing with the atom, that means it also has 17 electrons. So I'm going to draw the dot-cross diagram for sodium. So this is sodium, and it's got 2 electrons in the first shell. I'm just going to show those as crosses. You don't have to use crosses, you can use dots or anything else you want. And then it has 8 electrons in the next shell. And then in the last shell, it has 1 electron. Notice not very careful with my circles, but it doesn't really matter. Okay, so it has the electron configuration in terms of shells of 2, 8, and then 1. Okay, it tells us there's 2 electrons in the first shell, then 8, then 1. Chlorine has, again, the same 2 electrons in the first shell, and then it has, again, 8 electrons in its second shell. And last but not least, it has 7 electrons in its outer shell. Again, notice I've used crosses. You can use dots, you can use whatever symbols you like as long as it's clear that you've got the right number of electrons. So we can conclude from this that each principal quantum shell contains a fixed number of electrons. So principal quantum shell 1, which was our first circle, that contains a maximum of 2 electrons. The second principal quantum shell can take 8 electrons. The third principal quantum shell can take 18 electrons. And the fourth principal quantum shell can take 32 electrons. Okay, so you do need to know those numbers. They'll become a little bit clearer to you a bit later on. So in science, we need to be able to prove what we say. So we need to provide you with evidence that these quantum shells exist. After all, you can't actually physically see them. So we have to look for other pieces of evidence. And one of the key pieces of evidence we get is the emission spectra of the elements. Okay, so these are, you might have seen them before at GCSE, these colourful lines. So this is hydrogen at the top. It's got very few lines. Sodium, you should be able to see it's got very bright yellow lines here indicating that it's sodium. But what we're interested in this case is the fact that they are discrete frequencies of light. We don't get a continuous spectrum. We don't get every single colour of the rainbow. We only get specific frequencies. So these specific frequencies help us to explain why electrons exist in these principal quantum shells. Because if the electrons were not in shells, we would get a continuous spectrum. Because they are in shells, we only get specific frequencies. And those frequencies are to do with the way the electrons can be promoted or fall back. Now you're going to study that in a little bit more detail in flame colours when we do that with group 2 chemistry. But at the moment, the lines indicate the electrons moving between these energy levels. So for example, an electron moving from principal quantum shell 3 down to 1 might give off blue light, but 3 to 2 might give off yellow light. So you get different frequencies of light dependent on the energy gap between the shells. If the shells weren't there, you would get a continuous spectrum. In other words, the electrons would be able to absorb and emit all frequencies of light. They can't. They can only emit light at certain frequencies. And those frequencies are determined by the gap between the quantum shells. So a little bit more practice. So sulfur has 16 electrons, so it has 2 in principal quantum shell 1, then 8, then 6. Magnesium with its 12 electrons goes 2, 8, 2. Oxygen has 8 electrons, so it has a 2 and a 6. And argon has 18 electrons, so it's 2, 8, 8. Okay, now there is a slight problem with this idea that the electrons get completely filled up and then before they move on to the next shell. There's a problem with principal quantum shells 3 and 4. So you might have come across this with calcium. So 2 electrons go into principal quantum shell 4 before they backfill quantum shell 3. So if we look at calcium, it has a total of 20 electrons and it goes 2, 8, 8, and then the last 2 go into principal quantum shell 4. But scandium, which has electron number 21, in other words, 1 more electron, it goes 2, 8, 9, 2. In other words, the extra electron does not fill up quantum shell 4, it backfilling quantum shell 3 up to that total of 18. Now, to understand why this happens and why the periodic table looks like it does, we need to look in a bit more detail at the electron configuration. So far what we've been looking at is what we would call a GCSE model. And at A level, we need to go into slightly more detail. So as you would expect at A level, things are a little bit more complicated. So we have our principal quantum shells. So we have shell 1, 2, 3, and 4. But within those principal quantum shells, they can be broken down into what we call subshells. So principal quantum shell 1 only contains 1 subshell, and we give it the letter S. Principal quantum shell 2 has 2 subshells. We call them S and P. Principal quantum shell 3 has 3 subshells. We label them S, P, and D. And the 4th principal quantum shell has 4 subshells, S, P, D, and F. So that's our principal quantum shell, which is represented by a number, and then our subshell, which is represented by a letter. We need to break that down a little bit further. These subshells can be broken down into orbitals. Now, quite often we will represent the orbital as a box into which we're going to place our electrons. Okay, some of them do have letters, so because there's only one orbital in the S subshell, we just have it one block and we just call it an S subshell. P, well, there are 3 orbitals and we call them PX, PY, and PZ, and we'll look at those in a little bit more detail later on. So again, S has 1 orbital, P's always have 3 orbitals, and D's have 5. S always has 1 orbital, P, whether it's 2, 3, or 4, always has 3, D is 5, and F's the biggie because F has 7, which is why the 4th principal quantum shell can take so many electrons. There you go, 7. Okay?